Hi, my name is Anna Aguiar, and I'm going to show you our work on vehicular links with 802.11 AD. So this is an exploratory work. And our main motivation is that although 802.11 AD requires very directional antennas, and does have a hard time in environments with large amounts of mobility. It can also achieve very high throughputs, and so if you can actually just have a very short time for communicating, it can still be enough to exchange, for example, to update map tiles or to exchange information about detected objects in a cooperative perception scenario. So first, some brief background on 802.11 AD. It works on 60 gigahertz ISM band, which is a very high frequency. Does have the channels have very large bandwidths and can achieve throughputs up to several gigabit per second. The high attenuation requires that highly directional beamforming is used with smart antennas. And so any two devices always need to find out which is the best configuration of the antennas on both sides to achieve a good communication. And that is done with a sector sweep protocol. Okay? So that's what I'm going to show you briefly now. On the bottom left, you see the two representation of two stations, the access point and the client. All these pie slices represent the antenna sectors. So how does this work? The AP starts sending beacons on each of its own sectors, and the station is measuring the received SNR with an omnidirectional receiver antenna. This is called initiator sector sweep. The station can now choose or can know which is the best sector from the AP. And now it will send that information back in a similar manner. So by sending on each of its own antennas that information to the AP, and the AP, so these are the responder sector sweeps, which the AP is actually listening to also with an omnidirectional antenna. So, and measuring the SNR, so they can also choose the best sector for the station to use. It will then send that information as a sector sweep feedback to the station, and the station acknowledges it. And after this is the end of the sector level sweep. After this, both AP and the station know which is the best sector to use in their communication. So it might be difficult to do this with a lot of mobility, okay, although this is quite quick. So we took some commercial off-the-shelf devices, the TP-Link Talon 7200 AD, and mounted them on vehicles. One of the vehicles was static, and it had one device configured as the access point, and it was parked. It was parked actually at the location where you can see this video on the bottom left. Then we also mounted two other devices on a moving vehicle. One of the devices was configured as the station, so as the client, and the other device was configured in monitor mode. Okay. The channels was configured as a 2 gigahertz bandwidth, and we were sending UDP traffic at 1 gigabit per second. We were obtaining the positioning for the mobile vehicle from a smartphone and syncing devices via NTP. You can see on the bottom left also that this environment was quite simple, so there were not a lot of objects or buildings in the surroundings, and it was quite an empty street, although there were some lampposts and metal surfaces that might alter the environment. So these are, you can see our initial results after some pre-processing. So we chose pieces of the trajectories where the car was moving and the throughput was non-zero. And you can see on the left, the throughput can reach easily 500 megabits per second. And it can also do this for distances larger than 10 meters. On the right-hand side, you can see the throughput versus the vehicle speed. And here also you can see that you can achieve 300-400 megabits per second at more than 5 meters per second. So these were unexpectedly high throughputs, and we were asking ourselves what might have caused this. So first, let's look at a geographic representation of these high throughputs. On the left, you can see a heat map. So most of the samples we have with movement and high throughput are, of course, close to the access point. But you can also see here that there are these cells, especially in this street going up, that have quite a lot of samples with throughput. And if you look on the right side, there is a representation of the moving vehicle and the throughput it sees as it approaches and goes around the vehicle, the stopped vehicle. And in this case, you can see that there are always higher throughput values in this area. So this was a consistent behavior, and we thought it might be caused, so unexpected also, and we thought it might be caused by the rooftop of the cars working as a ground plane. Okay, a ground plane is actually a metal surface that you can place below an antenna, directly below the antenna, which sort of works like the Earth and thus sort of reflects the radiation pattern. So we took an aluminium surface, 1.7 by 1 meter, and put our client on top of it. We also put the access point at 1.8 meters on a wooden structure, and the client at 1.35 meters. Just to clarify, the thing you see here is not at 1.35 meters, but we did not have a picture, so 1.35 would be with two other tables on top. We measured this setup statically at 5 distances, ranging from 2.5 to 12 meters. We did 3 runs at each distance of 60 seconds each. So now, what does it look when we compare with results with ground plane with results without the ground plane? So in blue, you can see the results with the ground plane, in red, without. And you can see for each distance that the distribution of the measured throughputs is larger if you have the ground plane. So there is a sort of an increase in the performance of the link if you are using the ground plane. We actually, I'm not showing it here, but you see in the paper, we also did a paired test on measured SNR values on both cases, and you can also see a significant difference, so higher received SNR in the case with ground plane, but it's around 1 dB. Now, we also looked at the sector choices, although these are the aggregate sector choices, so all for each distance, this is the distribution of chosen sectors. And you can see that without the ground plane, it's very steady, and you actually only use 3 sectors, and it changes a bit with the distance, but it's pretty similar throughout. When we use a ground plane, the amount of sectors used changes, and it's much more diverse, and it also changes more as you change the distance, so it's much more sensitive to the angles. And so there is a difference in the radiation patterns caused by this ground plane, and this might indicate that there might be also this change in the radiation patterns on top of the vehicles. However, the differences we observed, as you can see here, in the throughput or in the paper of 1 dB SNR, they do not seem sufficient to explain why on the field we could observe several hundreds of megabits per second at 15 to 20 meters, and in the static environments, even with the ground plane, we could not reach any throughput. I mean, it was 0 at 12 meters. So right now we are doing the measurements with a more detailed setup. We are using a precision GPS, and we are improving the timestamping. We have improved the timestamping of the sector sweep frame so that now we will be able to match the sector sweeps to specific locations and throughput values. And we will also then follow up with redoing the static ground plane setup, but now using the same azimuths as in the vehicular setup for the high throughput locations. So thank you for listening, and it was. I hope you enjoyed it, and I hope we can have a discussion next week at MedComNet.